Okay, I think we're on. Good morning, everyone. Welcome to the first talk of the Cloud and Streaming track. I'm Marta. I'll be hosting the track in the morning bit of the conference. And without further ado, I'd like to introduce you to Paško, who is the head of engineering at Media Toolkit. He's tuning in from Croatia to tell us about their journey at Media Toolkit with Redis and how they are using it internally for scalable and robust data processing. And this will be a live talk, so Paško will be available at the end to answer your questions. So please drop them in the Q&A tab as he follows along, somewhere down to the right. And yeah, welcome, Paško. I'll let you take it from here.
Thank you, Marta. And hi, everyone. I wish you a good morning, afternoon, or evening. I hope that you are wide awake. For you that are in the morning time zone, that you got your coffee and you are ready to listen some great talks today. Welcome to the first talk of this track named Designing Robust Processing Systems with Redis. This will be the story of how we utilized the Redis database for maximum performance and minimized our costs. Why are we talking about this right now? Because we at Media Toolkit started about 10 years ago as bootstrapped startup. And this means that our infrastructure budget was very small and we were in a situation where we had to be resourceful. Get maximum out of what we got, but more of that in the talk. So a bit about me. My name is Paško. I'm head of engineering at Media Toolkit. Graduated in computer science field in the University of Zagreb, Croatia. That was quite a bit time ago. 10 years ago, and for the last 10 years I have been working in Media Toolkit. Here I had many formal roles and even more informal ones. I started as a software developer, promoted to senior software developer, then team lead, then head of product, and now I'm currently in the head of engineering role. On the side, I got stuck with DevOps tasks, HR tasks, and even some C-level tasks. But some of you may take it as a nuisance, but it represents a great pleasure to me to be involved in companies' organic growth and doing everything that needs to be done in that quest. Okay, let's start with some tech talk. Basically, after a few iterations and pivoting, we decided at Media Toolkit to build real-time media monitoring system. We wanted to build a tool that will constantly cover news and social media posts on the internet and let our clients to write some phrases they wanted to track in some sort of form of Boolean query. For example, notify me when this phrase is mentioned in text, but this another phrase is not at the same time. Additionally, we made some reports for our clients with aggregations and breakdowns of collected data of their interest. So basically, we will crunch those data in some actionable numbers. Something like Google Alerts, if you had a chance to play with it, but on the more enterprise level. So, sorry. We will crawl a lot of websites, social media, and anything we can put our hands on. We will do that on a regular basis and extract new content. We have started with a few hundreds of largest websites in the world and went to our potential clients to show them the product. And they told us, no, we want to know if some local news outlet is writing about us. If someone this big mentions us, we will know it in about an hour or so, and we will know it without your help. So we introduced ourselves very early with some scalability issues. We had to put hundreds of thousands of websites and social posts in our system and process them in real time. That is a lot of data that need to be processed. And I must also say that we didn't have experienced team in this domain. We all of us had couple of years of experience, and as we were bootstrapped, we needed to maximize utilization of our resources. So basically, with that in mind, we came up with architecture that should help us in building scalable and robust system. It was something similar to microservices architecture as we know it today. But bear in mind, this was like 9-10 years ago when microservices were just some kind of R&D architecture term, and good practices in building system like that were very scarce. It comes to mind Netflix or Amazon had some materials about that, about microservices, their take on architecture, pros and cons, but that was it at most. So as I said, we wanted to build horizontally scalable solution because we wanted to be able to scale with ease. And when need arise, we need to be able to scale. It was obvious at that time that buying another server instances would be the way to go, as we would exhaust physical limits with vertical scaling very quickly. Vertical scaling, just to mention, is when servers can contain only limited amount of RAM memory, and when your system reaches physical limits, you are in trouble. You cannot put infinite amount of RAM, CPU, or disk on your server. So we wanted to change our way of thinking from monolithic task to microservice architecture as we know it today. We wanted to split the work that needs to be done to many processes with much less responsibility and let them communicate with each other. Naturally, this communication would be done via queues. So after breaking down all the work that is needed to be done and drawing these smaller chunks of work on our dashboard, we ended up with something like process chain. Processes with limited possibilities that are connected with each other via queues. And all of these processes were part of the bigger picture, the initial idea, but now we have more manageable system. One process gets its task on input queues, does its thing, and pushes task in output queues. That output queue would be input queue of the next processing chain, etc. So we are building processing chain. Okay, we agreed that those input and output queues will be the focal point of our early architectural decisions. Those queues can be of two types. We said we introduced streaming and circular queues. You can probably guess from the names what is the difference in those queues, but I will tell it anyway. Streaming queues are queues where tasks are put to queue once and removed from queue for processing. Tasks are in the queue only once and don't come back anymore. Circular queues are queues where tasks repeatedly enter the queue again. They go to processing and then those same tasks are returned to the same queue to be processed later. In addition to that, we introduced scheduled tasks. Tasks where we can specify the exact time when we want to process it. And after we have defined what our needs are, we had to make a tough choice. What technology we should rely on in implementing queuing? 10 years ago, I was active stalker of open source tools and databases at that time. And I was acquainted with Redis, and I dug deeper in the documentation for potential solution. I immediately liked Redis for its simplicity but great performance at the same time. I wanted solution to be as simple as possible so we could replace it with something more complex if need arise. Of course, if you lock yourself on something complex at first time, it would be a much more trouble to switch to something else. Intuitive, but worth to keep in mind when making these decisions. So basically, Redis is in-memory data structure store. It contains simple yet powerful data structures as lists, sets, sorted sets, and many more. It can be used as database, message broker, or as a cache. In-memory means that it resides in RAM memory by default, so operations will be very, very fast. Also, it was easy to maintain, upgrade the versions of Redis, test performance, play with various options. It all went smoothly and seamlessly. And last but not the least, it had very active community gathered around its creator, Salvatore Sanfilippo. His alias on developer forums is Antires, so big shout out to him. He was there for questions, discussions. He was actively dealing with bugs, issues, and feature requests. For example, I was sold on him one time when he knew how to say no to some voted feature to keep the stability of the code base intact. In startup ecosystem, that is everything you can ask from a guy that creates technology you plan to use. So he was thinking about stability, and I would like to suggest to anyone who is even mildly interested to read his blogs and his development. His blogs he wrote in his development of Redis. They are very clear and they can give you a lot of introspective how to build a good technical product. Okay, so after this brief introduction to Redis, let's get back to our proposed architecture. As we said, we needed to implement streaming and circular queues with option of scheduling tasks. Let's see here how we did that with Redis. Let's start with streaming queues. We represented them as list data structure in Redis. It is ordinary list. That list is our queue, where we can add the task with lpush command and remove task from list with rpop command, as we can see here in the example. This is a screenshot of the Redis client directly on the server. With those two commands, we have implemented first in, first out queue. Circular queues, once again, are queues where same tasks keep returning. Technically, they are implemented in the same way as streaming queues, only semantically there is a difference. Circular queues are simultaneously input and output queue of the same process. Okay, and as we said, we need to have scheduled queues so we can have the mechanics of activating some tasks to execute at precise moment, so we can have predictable temporal behavior when we need it. We accomplish that with sorted set data structure. So sorted set, this is like an ordinary set, but every element has its own score by which the ordering is made. So we did a little twist here. So our tasks will get the score in form of the timestamp when we need when we need the task to execute. So in this example here, we put some task to scheduled queue, some scheduled task to queue, and as score we put the timestamp when we want this task to execute. So this is this z-add command. So we put task to queue with the timestamp here. After that, second command is from process that reads from queue. Command in pseudo sounds like this. Give me all tasks that have score between 0 and current timestamp. So this is what this second command suggests. In that, it does. In that way, we will get all tasks that needed to be processed by now. And after that, last command is to remove these tasks from queue, so they can't be read again by other instances of that same process. For this, we need some transactional power. Redis has convenient commands that can assure that commands are executed in transactional fashion, but also it has Redis scripts. Those are scripts written in Lua language that are transactional by default. So basically, we are writing small Lua scripts to get scheduled tasks from input queues. Okay, Now we go to now when we have seen how we can implement the queues with Redis, we go to take a look to our architecture of some sort. It is simplified process chain. Processes are annotated with P's and queues with Q's. Every process has its state beside it. This place sign in the boxes means that processes are running, they are getting inputs, producing outputs, and everything is going great. Here we can see that process 1 has one input queue and two output queues. As one input queue is the same as the output queue, this makes it a circular queue. Real example of some process used with circular queue is our crawler at Media Toolkit. This would be a very stripped down version and example, but basically tasks this circular queue contains are URLs that we need to crawl. Queue is scheduled, so we can have control over when we want to crawl specific URL next time. So we can delay it at will to avoid bans, IP blocks, and I don't know, denial of service, unintentional denial of service, or something similar. So think of process 1 to go through this scenario. Collect tasks that are URLs that are scheduled to crawl them, which means download the HTML from URLs. After that, send that HTML as task to other process 2, and send URL back to your input to be crawled in 15 minutes or at any time you want it. Process 2 receives task, it processes an HTML and has 3 output queues where it sends appropriate tasks, and so on. We are making the chain. Process 7 and process 8 are processes that don't have any output queues. They usually persist something in database or doing something similar, and tasks are not propagated further. So basically, we can see here that processes can have multiple input queues, like process 1 or process 8, but also multiple output queues, like process 2. Okay, now when we have seen some basic example with chain processes and queues for communication, we plug it in the real world. Of course, in the real world, a lot of unexpected things happen. As we scrape the content all over the internet, a lot of unexpected inputs can make part of the system to fail. We use contracts, interfaces, defensive programming in that situations, but every now and then happens that some input breaks some process. Aside that, hardware and network errors are a common thing that we experience. And by far, the biggest reason for the outages are human errors. Of course, you try to minimize this with tests, with some other things you can do here, but it's natural that errors happen, and it's better way to think about it that we must adapt our system to be resilient in those cases. So not to trust the process or the humans to correctly implement that process, but we must defensively program our system. In our architecture, we must make sure that all tasks are executed, preferably once. We could sometimes deal with possibility of processing the task more than once. We try to make our processes idempotent whenever we can. That means the same task executed twice won't change the final state. But something we surely must do is to prevent our system to drop tasks. So we had to come up with idea how to keep our tasks stashed somewhere until we are finished with processing them. After processing, we can delete them as they don't matter to us anymore. This is why we have introduced backup queues. These are Redis queues that hold tasks that are currently processing. Scenarios like this. Process starts and checks whether there is any task in the backup queue. If there is, it starts processing those tasks. If there isn't, process takes tasks from the input queues. When it takes those tasks, it persists them in the backup queue. After processing, tasks are removed from the backup queue. To give you a visual of this that I was speaking about, here you can see a process that is currently processing 3 tasks, T0, T1, and T2. At the same time, these tasks are residing in the backup queue and are deleted only after task is processed. If something happens and process crashes in the middle of processing these tasks, after restart, those tasks will be waiting in the backup queue to be the first to process. Okay, yes. So we have dealt with issue of losing tasks. In this case, some process crashes. But with this, we have introduced another problem. Let's say our input task is malformed, or we serialized the message badly, or something like that, and our process crashes on this input. What we have now is that this problematic input will always reside in the backup queue of the process. When process restarts, it will take this input and crash again. We have a crash loop now. When process is unable to consume its input tasks, its input queue will get bigger and bigger until our Redis server gets so big, it consumes all the available memory. After that, kernel will crash Redis, and in some instances, even our whole server could become unresponsive. To deal with this problem, we have introduced back pressure algorithm. To picture this, let us see our system architecture. Let's say that our process P6 has had some bad input task and it is stuck in the crash loop. You can see it with those little image of not going well. And also we can see here that the rest of the system is behaving normally, not phased by this crash loop at all. As a result, we have situation where Q8 is empty and Q5 is getting bigger and bigger until whole our system crash. All other processes and queues are behaving normally. This, of course, is very dangerous state that we must avoid, so we introduced back pressure. Back pressure is a concept I'm sure you are mostly familiar with, but it's a concept where information about outages in the system can be propagated to all the processes in the system, so you can have deterministic behavior and, in this specific case, bounded RAM usage of RAM memory. Our back pressure algorithm is made like this. We have one special process that has all the information about process chain. It knows what processes are connected to what queues, and this process constantly checks size of all the queues in the system. If there is any queue that is bigger than the size limit, pause all providers to this queue. Send its signal to all providers and all instances of providers to pause, not deal with any of the tasks. If queue is under the size limit, tell all providers to continue with processing. This way, we are assuring that there will be no additional tasks added to queue after there is a size limit breach. Some chaining can get us to conflict situation. For example, one process can have 2 output queues, and it could get mixed signals. If one of those queues is full and another one is not, it can get pause and continue signals at the same time. In that situation, we always pause the process. This type of defensive design that is of great importance here. Better be safe than sorry. So here we have Redis commands for getting queue size. There are trivial commands. Len, which is short for list length, is used to get the size of the list, and that is our streaming queues. And zcard gets cardinality of sets, in this case sorted sets, and these are our queues that contain scheduled tasks. With back pressure implemented like that, we had accomplished few things. When some outage occurs, every queue grows to expected size, not more than this. We can then calculate and we know what is the worst case scenario regarding RAM usage and how much of memory queuing will use in those situations. Other thing is that part of the system affected goes to hibernation. We can save resources, but not running that part of the system until we fix the issue. Of course, we can have another strategy here. For example, you can put inputs that are causing the crash to some dump queue to deal with this later. But we have decided to implement this hibernation strategy. As I said, we had to be resourceful, and with this strategy, we resolved all the possible causes, not just broken inputs, but also network crashes, hardware malformations, and so on. To put this, what I'm talking about, in the context of our architecture, we saw that process P6 has some trouble with malformed input, and we are in danger that Q5 grows until out of memory occurs. With back pressure algorithm, we have this scenario. If process 6 stops working, Q5 grows until its size limit. And after that, process 3 pauses and its output queue is full. As its output queue is full. By doing that, we let Q2 grow to its size limit, after which P2 pauses, Q1 grows, P1 pauses, and so on. And as process 2 pause, there is nothing to provide tasks to Q3 and Q4. So processes in those branches are idle, waiting for new tasks. We can see here that this is like domino effect, what back pressure in a nutshell really is. Queues are getting full all the way to the beginning of the chain. Certainly better than the alternative of kernel killing our Redis server. Okay, so we have seen how we can bound our system. But the question remains how to implement those pause and start actions for the processes. For that, we have used, you guessed it, Redis. Redis can be used as a message broker. Specifically, it has publish-subscribe pattern that can be used. Why is this pattern great for us? It is because we are designing system to horizontally scale. We can have multiple instances of the same process available on different machines. Every instance of that process will subscribe to the control channel for start and pause messages. As we said before, we have one process that is monitoring queue sizes and controlling processes. When some process and any of its instances need to be paused, process controller broadcasts a message to a channel. And that message is going to every subscribed process. So here, we don't need to worry about keeping track of process instances and where they are running. They can run anywhere. If process is running somewhere, it will be subscribed and it will listen for the control messages. In Redis, we have two convenient commands, publish and subscribe, which are pretty much self-explanatory. We can see here example via Redis client where we subscribe to a channel. So basically, first window is telling us how we can subscribe to some channel, and we see that that client is in state of receiving messages. Control message 1 means that operation was successful. In another client, we publish to this exact channel some event. And what we can see in the first client, that it receives a message where it said in which channel what event was broadcasted, and we can act accordingly. Okay, I'm going to show all of this in our architecture in some simple way. Basically, here are shown multiple instances of the same process and process controller. Every process during startup subscribes to a channel where it would get its control messages via subscribe command. implemented in Redis, of course. Also, there is process controller. As we said, this is process that monitors the size of the queues and acts by back pressure algorithm. When some control message needs to be sent to every instance of the process controller just publishes one message to the channel with publish command, and every process that is subscribed gets that message and can act accordingly. Okay. After this, we will talk a bit about the numbers. I will just put some numbers into perspective to see how massive system we have managed to implement. In the course of 24 hours at Media Toolkit, we are collecting about 40 millions of articles and social media posts. So basically, news outlets, Twitter, Facebook, Facebook page posts, YouTube mentions, Instagram, and much more social media. We are also analyzing, filtering, and storing every one of those articles, so it's very data intensive. Also, we are sending about 10,000 emails and 30,000 notifications per day to alert our users that something of their interest is mentioned somewhere on the internet. Of course, if this seems interesting to you or this use case of tool is relevant to your interests, you can always sign up for a free trial if you are interested on mediatoolkit.com. So basically, in conclusion, we have achieved multiple things with Redis. Our system can scale horizontally because of the queuing and publish subscribe pattern that we described before. With back pressure algorithm implemented, we have memory bounded system without fear that Redis will grow without control and potentially cause us data loss. One thing that comes to mind is how performant is Redis. I can say from personal experience, it is very performant because it resides in RAM memory. Commands are very quick in the most cases. We are using Redis in multiple ways, and stuff in this talk is just one of the things. We have isolated one Redis instance just for these things we talked here, queuing, controlling messages. And there we are making up to 50,000 commands per second, which is more than enough for even for biggest spikes in our system. It has very low resource footprint. We have near 1,000 queues and 400 or 500 processes going 24/7, taking and putting tasks into various Redis queues, pausing, restarting, continuing with processing, and all that. For all this, one CPU and 15 gigabytes of RAM are more than enough. One CPU, because Redis is single-threaded, so you won't need to assign a lot of power to it. Also, it's very portable. It's basically key value storage. And as I said before, it can be used as a cache, very fast caching mechanism. So you don't need to have some additional data stored just for technology's sake. And last but not the least, Redis is very easy to manage from the DevOps perspective. It's very easy to run your tests on, upgrade to newer versions, and everything else you need to do to manage it efficiently. With all this, in conclusion, it is easy to see how Redis is small and simple enough, and at the same time very powerful to bootstrap your startup on. Of course, there is, not sure how old, but let's say it's old saying that goes, what got us here won't take us there. Meaning that at some point you will have your requirements really specified and you would like to make use of specialized technology for some problems. And that's okay. For example, we started to use Kafka instead of Redis when we were sure that good thing for us is to sacrifice simple solution and portability for features that we can't get with Redis, or they are more easily implemented. But if we decided to go with Kafka or something like that, some technology that is really specialized 10 years ago, we might have been forced to change our requirements just to meet constraints that specialized tech require. So my take on this is that you start to build your system on a simpler technology and then gradually grow to more complex specialized tech. Redis is perfect for that initial phase for its simplicity, but it is also very powerful, so you can continue to use it for the most of the use cases you may have. Okay, this will conclude my talk. I got 4 minutes earlier, ended 4 minutes earlier than allotted time, and thank you for listening. Marta, hi.
Paško, thank you so much for sharing your lessons learned with Redis. There is one question at the moment. I also had a question, but you kind of answered it in the last slide. So if you want to take that and then conclude.
Yeah, I think that this question here, event persistence of queuing system, and I talked about this in the last part of the talk. So basically, Redis is not a Swiss knife. It's a technology that can only get you so far. Bear in mind, I'm not talking about the state of Media Toolkit Tech now, but 5 or 10 years ago, when something like this was basically not a good way to go, because we didn't know what we actually needed at that time. And when our requirements were more specific, we surely switched, especially for queuing system, we switched to Kafka. And we had some issues with Kafka that we overcome with Redis in parallel. But basically, point of the talk is that you gradually increment your scope, especially if you have some startup, you are in startup world, which you don't have a lot of time or a lot of resources to implement something from the start, from the beginning, that is on the enterprise scale. Okay, I think that answers the question. Anyone wants to ask another question, maybe? Okay, if not, Marta, I will hand it over to you. Let people to grab some more coffee, because at some parts of the world it's very early or very late, so coffee would be needed throughout the day.
Yeah, thank you, everyone. If you have additional questions or you can think about something later, just hit Paško up on the conference Slack. I'm sure he'll be around to answer more questions. Thanks a lot, Paško.
You're welcome.